Today the lecture is about multimodal alignment. This is a very interesting topic because this is what, if you ask me what from all the 5 general challenges in multimodal machine learning that we discussed early in the first week, multimodal alignment, like synchronization between modalities, is probably one of the most multimodal or multi-view of all of them. Representation learning, which we discussed last week, is very important. Good representation is important, but this is also something that's important for many machine learning cases. But alignment is very key to multimodal. And this will look at different type of alignment, implicit and explicit alignment. For explicit, we'll look at dynamic time warping and some extension. And for implicit, we'll talk about attention models as examples for that. So multimodal alignment, we discussed it in the first week. This is the idea of finding a relationship and correspondence between 2 and more modality, but within a modality, we have elements in each of these modalities. If it was a series, a time series, there's sample, time samples, maybe, and for each modalities. And the alignment is about, it's at the level of these elements, like trying to link these together. Some may not link with other modality because they're unique to that modality. Some of them may be redundant, like the same information is in both modality, or some of them could be complementary. Meaning the 2 of them together from both modality start bringing a new meaning intent on it. And the 2 type of alignment techniques that we'll study are explicit and implicit. The explicit, the loss function, what you're optimizing is the alignment. Your goal, the task is the alignment. And so this is for the explicit. The implicit means your loss is something else. Maybe you're predicting emotion, sentiment, or something like this. And the implicit is like, to solve this, you will need to be able to do the alignment. So often you will do maybe some level of representation learning, and then alignment, and then eventually your loss. So the alignment itself will be latent. We'll discuss next on Thursday also how representation learning and alignment could be done at the same time. But today we'll see them as 2 separate cases. So examples for both explicit and implicit. So images and captions. So you have the image, it has many objects in it, and you want to be able to align it with the words of the caption. Or you're watching a video, a how-to video, and you want to align maybe the recipe with the segments in the video. Or in the case of phrases, like in the machine translation case, which is not multimodal, but it is a multi-view. So explicit alignment, the goal is to find a correspondence between modality. This is what the loss function, and the example for that is sometimes you may have an audio track, and then you have the transcript, and you need to do what's called word alignment, aligning words, which are tokens, with the audio. You may also have 2 videos and they're out of sync, or they're what's called co-reference resolution. Co-reference resolution is in the language, but co-referring expression is also in the multimodal. So here in that case, we'll be assigning the words with the language. There's different version of it. The co-referring expression task usually means only one object is linked with the whole sentence, but there's also other tasks where the goal is to align every object that are mentioned in the image. That's another task that you can do. The implicit is probably the most popular, and that's where we'll spend the most, both on Thursday, and we'll also discuss it even on lecture 7.1, when we also talk about module networks and things like this. But the implicit means that I have a task, and my task itself may be something like image captioning, But as a step, intermediate step, I will intermediately, as a middle step of this, link entities from the text with entities in the image. And that can be done through like a discrete case, or it could be done more in a continuous sense, semi-continuous, like a attention model. It's still somewhat discrete, but a little bit more continuous. So machine translation, cross-modal retrieval, image captioning, visual question answering, all of these are using these intermediate representation, intermediate task of linking entities from the different modalities. And one of the key approach, or at least that has been studied, is the attention models. But let's start with explicit alignment, because that may be the one you've never like directly worked with, but I think is important to know when you start looking at alignment. So let's say you have multiple videos, maybe a video in 2D, maybe you have motion capture, and you have also some other version of this, maybe in 3D, 3D of the person or just the leg. And your goal is to align them. Or maybe you have two videos. You have a video of LP kicking the ball, and you have a video of someone else doing a similar action, but not exactly the same action. And the challenge here is that it may be not a one-to-one, not every frame will be matched. Like some frame may be matched to multiple frame in the other modalities. In a very general case, some frame may not even match to any of the frames here. But as a first step, let's suppose that every frame matches to at least one of the other frame. That's the first assumption we'll make. And so if we have, in this case, we have two underlying time series. And so the first time series and the second time series may not have the same length. They will have different length. For now, let's say that they're represented with the same number, but that's not needed. So they could be from different, different dimension. But now let's suppose that it's a unimodal case, and so that they are represented the same way. And so, but they have different length. And so you want to match, you want sample of one sequence with the samples of the other. And just for simplicity, I presented visually the same sequence. So one way to formalize this problem is you could define a loss function that find the set of indices to minimize the alignment difference. So the indices will be, the vector p will be the same length as x, and the vector pty will be the same length as y, the y vector. And there what it will be is we'll just say which index to use. And then the goal will be with some kind of, for example, a Euclidean loss, saying that at the end of the day, I want this to be as small as possible. Let me find my parameters, my model parameters are those indices. And so if the index is 1, that means that I'm using the first sample. So here for x, it will be 1, 2, 3, 4, 5, 5, 5, 6, 7. And for y, the optimal will probably, in this case, what I showed, 1, 2, 3, 3, 4, 5, 6, 7, 8. Okay, so that's what pty will be, the optimal, at least the one I depicted it, and ptx will be. So where are these vector and where ptx are the vector the same length? So sorry, I mentioned a second ago, I said they're the same length. What I meant is not the length, the vectors themselves will be whatever the longest sequence will be the longest you could be here. But when I said length is that ptx could have a value from 1 to nx, and pty can be value from 1 to ny. That's what I meant. And one of the approach for that is dynamic time warping. And I don't know how many of you have worked with dynamic time warping. The idea of dynamic time warping is to find the lowest cost path in a cost matrix. So starting from maybe 1, 1 to nx and y is like, how can I get from one point to another? And there's the optimal path I could use, but there's also many different other paths I could use. And so when I do dynamic time warping, I want to do it in such a way, and that's we'll say a weakness maybe, but also makes it more efficient, is like a monotonicity, meaning there's no going back in this, the kind of dynamic time warping. There's no gaps, and that's maybe one of the downside of the basic dynamic time warping, is that there will be no gap, meaning every element will be mapped to something. And often to optimize, you'll have boundaries condition, and then you don't want to get too far. Often you will have a warping window, and then do not insert or skip too much, and so you'll have some of these constraints as well. To solve it, you in fact end up doing what is known in optimization as dynamic programming, while respecting those restrictions. I will not go in the detail of the optimization, but you could imagine it as exploring this path of all possible paths, and dynamic programming will be an efficient way of finding the optimal with the lowest cost in this. So this is the formulation, I will say the typical dynamic time warping formulation, which will be allowing us to find these indices in an efficient way. But you could also kind of unwarp these two signals and just unwarp it in such a way that they have the same length. And then if you do this, then you get to that really nice situation where you can have a matrix. And so now it's no more the indices that will define, that's what will be the parameters, but the main thing you will be searching for is that matrix that matches X and Y together. And so if you formulate this way, and that's a really nice formulation that will give us a lot more flexibility, is that you will find your X vector matrix. And if you remember, this may be of size like D times NX, and multiply by your WX, and we'll put some constraint maybe to keep it in a form as you see it visually. If you multiply the two together, then I will get in the similar space that if I take my Y matrix and multiply by my WY. And so if I do this, then I will get a nice loss that in this case, I will often use like something like the Frobenius norm, although this could be changed, it's not a requirement, but a good representation will be. And now what's nice is what's my WX and O and W, we know these a lot more. And so we can play with these, because then we're in the world that we know better, WX, WY, it's a world we'll know better. And so how do we work? And so one of the problems with dynamic time warping, as I said, is maybe the complexity, but it may be sensitive and it's unimodal. So even if you do that other representation that I talk about, this can be optimized, maybe linear least square or something. We can optimize this, but it's still only unimodal. And so how do I go? And what if I have X and Y are from two different modalities? Oh, okay. So D, the dimension from Y, and maybe not the same dimension as X, and the space of Y may be different from the space of X. But what did we talk about last lecture? How did we manage to do coordinated representation? What was this one approach for coordinated representation that we studied? CCA, canonical correlation analysis, was this one way that if you have two modalities, and you want to learn a space where they're the most correlated, that will allow us, to find that space where the two modalities the most coordinated. And then after that, hopefully we can do the matching, the alignment. So canonical correlation analysis may be a good way. And if you remember, canonical correlation analysis, the reason it's called that way is that it's more than one correlation. We're finding many different projections, the way the text and image could be correlated. But what makes it canonical is that these will be as simple as possible, and simple in the sense that they're orthogonal to each other, these projections. So if you take this and you take the CCA loss and you put it in a matrix format, then you can also visualize it this way. I take X and I project my X into the HX in such a way that the projection of V is also the most close to each other. And if you do this with the same kind of constraint we talked about earlier, then we have the same correlation loss, a CCA loss as earlier. It's just earlier in earlier slide we had it slightly different here, but these are equivalent formulations here. Why will I go through this slightly different formulation? Is that now I can take the CCA and the dynamic time warping and put them in one formulation. And that was this great paper from De La Torre about U, which is a warping. U is about like bringing the U is about not the warping, but about the projection. Projecting my X into a space that is correlated with my Y. So I project Y with V, X with U, and then WX and WY are there to do the alignment. So within the same loss function, I'm able to do my projection, which is in a sense almost my representation learning, and my alignment together. And so we're able to do that coordinated representations that allow us to then do the alignment. So this is the canonical time warping, and this is optimized by coordinate gradient descent, fix one set of parameters and optimize the other. That's the chicken and an egg kind of optimization paradigm that has been done quite often. So when you fix WX and then you want to optimize U and V, if you remember to optimize U and V in the CCA, we could use some version of eigen decomposition or SVD. And then if we want to optimize WX, WY, you could use then any optimization. In this case, maybe we'll do it not at a batch level, but over all the data, so you can kind of Gauss-Newton kind of optimization over this. So this is the approach for canonical time warping. And now I'm asking you, how can I generalize to multiple sequence, all with different modalities? And so if you want to generalize to multiples, where you have multiple sequences and there, so I will say, let's say you have a video and you have also maybe acoustics, and you want to be able to align these together. Then in this case, you can just extend the same formulation. But here, the problem is canonical correlation analysis is usually working only when you have the typical canonical correlation analysis was mostly working only when you have two modalities, but the generalized version of it allows you to expand that, and that's what this paper was doing. That was really nice. And so when you do these approaches, then that's nice, because then you have multiple sequences and you can align these together. But even if they're from different modalities, you can try to align these different modalities, like body 2D, or in fact one is one hand and the other is the other hand. These all comes to can be aligned with this. So canonical time warping, it's a linear transform between modality. Okay, so up to now we were having X and Y, and we had a linear projection, and once it's linear projected, and you have also the WX, WY to do the alignment. Now, if I say, how can I make it non-linear? Probably you thought about it, the deep canonical time warping. So now the way to do the like something like CCA will be to do it in a deep version of that. And so so it can be seen as both a generalization of deep CCA and generalized time warping together. And that's what this deep canonical time warping explore and that. So this is a lot of things that we studied and talked about last week about CCA, but now merged with this point of doing alignment explicitly. And to optimize this, then you will be the same way that you optimize the non-deep version, where you do it solve for alignment with fixed projection, and then on the other side, solve the projection given the alignment. And there, since it's a deep representation, often we'll use more of a gradient descent. So this is the first approach on the deep canonical time warping. There's been extension to that a little bit, but this is, I will say, the one thing, if I'm talking about aligning, and this is the loss function, how do I align my two sequences? Dynamic time warping is a very key one that's been there for a while, but still very efficient. But in many cases, I don't have it's not my loss, it's not my direct goal. I want it. I still want to do it. I still want to improve on this. I want to be able to do alignment, but the loss may be something else, maybe about image captioning, visual question answering. And so in this case, we will do the implicit alignment. So it's more like a hidden. And so can we instead encourage the model to align, but this will be more of an intermediate step. And there's been quite a few approaches for that. And we'll discuss around week 8 or 7. We started a bit in 7 about graphical models as one other way to do alignment and to study how a random variable are linked together. But for today, we will look at a gating mechanism. If you remember LSTMs and gates, we'll look at an extension of this idea of gating that has been named and very successfully named attention models. Attentions are a gate, like in an LSTM you have a gate. So these weights that are the output of the attention will be dynamic weights. That's when you say it's a gate. It's should think about it. One way to think about it is like a dynamic weights of this. So so the attention model is the intuition behind it is that although let's say there's an image in the displayed image, the eye will, through the saccade and the fixation, will be focused on a subset of the image at any point in time, and then the rest will be will have either less or no associated sensing happening with it. In general, it still has some peripheral, but it will be less information gathered there than in the center. So this foveal vision we only see high resolution, about 2-degree vision, but because we move very quickly, we do pick up a more englobing vision of the image, but the foveal vision is a very high resolution in the middle of that. You could talk, I could talk a lot longer about attention on the human side, also the offbeat of attentions, where we are always in constant move. And although it looks like we're fixating one thing, it is often that you will move around, and that's a very interesting aspect of human attention. But for now, let's suppose we'll take this interesting and very complex aspect of human vision and simplify it with saying that humans are focusing on a subset of the image or subset of the information at any point in time. So certain words or certain part of an image, and this is also relevant even when you are also listening. We are able to focus our attention on a subset maybe of the frequency band, or to be able to pick up a certain person talking and maybe ignoring the white noise, for example. So the attention models are kind of taking this intuition and then expanding it. And the idea is to be able to have in between kind of your representation learning and your task, like your loss, to have these steps of aligning information together and be able to focus dynamically what information is relevant for my task. It will also, although there is this wonderful series of paper that one of them is already, I believe, a reading assignment, and I really invite you to read the papers before and after that one. But there is attention interpretable. That's a very interesting. And then there's attention is not interpretable, and attention is not interpretable is the paper I suggested for reading. So there's a really interesting debate in the community on this interpretability. But for now, let's say that attention gives a little bit more interpretability than not having attention. So let's just start with that claim. Recent attention models, there's been quite a few, and I would like to kind of categorize them in at least two or three categories. One is probably the most popular, is like what's called soft attention. So let's say you have an image, you will kind of wait where to look at. You're not going to say, hey, I'm only going to look at this eye of LP, but more like, let me focus more on the eye, but I'm not going to ignore the rest. It's going to be kind of a smooth one. And you probably got the intuition that having a soft attention will allow me to be easier for like optimization. Like, so it probably will help with the gradient, for example, if it's a smooth. Another very different view of it, which is probably different from many of you have thought about of attention if you know about it, is a transform network. Is like you get the image right now, and I'm not going to try to focus. Instead, I'm going to warp the field of view to be only into the place I want the information. And this is most relevant in the image world, although you could imagine extending it to language and multimodal. And the one that is the extreme, and I will say it's 1, 2, 3. 1 and 3 are definitely related. One can be the soft and the hard attention. 2 is not, you should not see it as in the middle, like it's an intermediate or a hybrid of those. The number 2 is really a separate way of looking at this, at least from my perspective. But a hard attention is the idea of looking at a specific set of the image, and often this can be modeled through a stochastic process and optimized through reinforcement learning. We'll discuss more about reinforcement learning in week 9, but at least we'll give you a first version of this, an example of hard attention. But the core of it is the soft attention. That's definitely has been the main topic for a while, and the extension we'll talk on Thursday is about like self-attention as an extension of that. But as a way to explain attention, and also because historically attention, the first attention was published on machine translation. So I talk both from an historical perspective, but also because it's a slightly simpler to explain with machine translation. Let me explain the problem of attention with the machine translation. So machine translation, the idea here is I have a series of tokens like words, and I want to translate from one view of the problem, one language, into the second view, like the second language. And so in this case, there are 4 words, 4 tokens, 4 samples in the first modality. In the second modality, in the generated one, we'll have 5 tokens that are generated. And as I mentioned, it's not a multimodal, but a lot of similarity there to the multimodal. So just to remember how we can do sequence to sequence, because this is one sequence and I want to generate a new sequence. So just a quick reminder from about 2 or 3 weeks ago about how the RNN were modeled. And so a quick reminder about encoder-decoder framework. So le chien sur la plage. And so I'm going, in fact, the opposite way in this example. Sorry for the confusion. I'm going from French to English here. So le chien sur la plage. I go from le chien sur la plage. I could have pre-trained that, maybe just that encoder just on French data. I could have pre-trained how to encode maybe by taking like one sentence and try to predict the next one. It's kind of similar to the word2vec extended to sentence level. And you can, or I could, and at the end of the day, if I train that, I get an embedding of my language for French, and then I can use that to be able to start as an initial seed to generate my words, and then generate the next word, and going on until there will be, in fact, there will be one more prediction for the end token. And so this is the typical sequence to sequence model. But the problem here, what are the problem, is that the encoder hidden state capture everything in the sentence. And so what's very challenging here is you get possibly, if it's a short sentence, then the RNN hopefully can get all of the information you need. But if for some reason it's a long sequence, and so you want to be able to not only be able to encode everything, but maybe we'll use some mechanism like an attention to, in fact, focus on a part of the sentence at a time, because encoding a full sentence can be an issue. A second issue sometimes is if you have a very long sequence, it's possible that RNN may remember more certain part of the sentence, specifically like the late part of the sentence. You could solve some of it by bidirectional RNN, but still a challenge. So if you have something like a sentence, the agreement of the European Union Economic Area was signed in August 1992. L'accord sur la zone économique européenne a été signé en août 1992. So if you have these and you want to translate such performance, how can we do it in a more efficient and hopefully more robust way? And this is what this landmark paper did. And so the idea, and I will do it step by step, but before encode, we'll just take the final. So usually we'll just take the encoding of all the words and take this endpoint. Here, we're not, maybe we still use an RNN to encode each of them individually, but we're not just going to use the last one. We're instead going to say, hey, every word are important in itself. And then what I will do is I will take a seed, and a seed could be as simple maybe as a start token, like a token start. And I will say, hey, what are the words? Which word should I focus on as a starting point? And probably as a starting point, I will start with the first few words. And so I will use a module, this is shown in blue here, which is going to weight. I'm going to say, hey, let me associate a weight with H1, a weight with H2, a weight with H3, a weight with H4 and H5. I'm going to associate a weight, and then I'm going to do a weighted average, very simple. And then that weighted average will just give me V0, not V, Z0, sorry for that. And so what you get at the end is just a simple weighted average that says, hey, this embedding of le, this embedding of chien, I'm adding them together, and those will have, let's say, very small weight. And then this will give you the context. And now I will use this to predict the first word. Now I use the output of this predicted word and say, now that I predicted the word dog, what should be, which word should I focus on? And now I will have a new set of weights for it. That's why they're called dynamic weights, a little bit like a gate. That's the same idea of a gate in LSTM. I'm going to gating. So I will say, hey, dynamically weight each of them, sum them, weighted average, give you a new Z, and then use that to predict the next word. And then take that one and as a new seed and decide new weights and then a new Z.